Hello everyone and welcome to Medford Anywhere Learning TV. We're glad you're tuned in. We want to give a shout out to our friends at Southern Oregon PBS, KTVL, KDRV, and the Dove Network. Thank you for hosting us on your station.
Hi there, I'm Robert Black. I'm the planetarium director and the astronomy teacher at North Medford High School. I'm glad to be with you today, and I'm going to be teaching a lesson on the past, the present, and the future of black holes. How's that for a topic? My target audience today is going to be high school juniors and seniors. Those are the kids I've got in my high school class. But I'm hoping to make this interesting enough that everybody, the old, the young, every age group is going to be interested in this story of black holes. I want to kind of weave this into a story. And my story is going to star a few famous astrophysicists. And of course, some of those astrophysicists are, of course, Albert Einstein, Carl Schwarzschild, Stephen Hawking, John Wheeler, and a modern-day phenomenon, Tiziana de Matteo. She's been doing some great simulations working with black holes and their effects on the future. Now, what we need to do is we need to go back to 1915. So this is over 100 years ago. Einstein did his famous work on general relativity. He modified what we think of as gravity. Newton, the master who coined the term gravity, said that gravity was something that reached out and pulled on things, that had this invisible tether, right? Almost like the tether ball attached to the pole where it's swinging. Planets are attached to the sun, the moon's attached to the earth. But his predictions wouldn't work if anything got near a real strong gravitational field. So along comes Albert Einstein, almost 350 years later, and Einstein looked at gravity differently. He looked at it as more of a depression, a well, a kind of a warp in the fabric of space-time. Something might be hard for you to imagine, but all experimentation says it's out there. So with Einstein's great treatise in 1915 comes along one of these mathletes, you know, people that use their minds, that love mathematics. And that, of course, is Carl Schwarzschild. Schwarzschild was a pen pal, a friend of Einstein's. He was actually working through some of the equations of general relativity, and guess what? He started working with massive objects, things more massive than the sun. And he took an object 20 times the mass of the sun, and he somehow magically would compress it, crush it down further. And he crushed it down to a point where, to escape this body, you would have to travel faster than light. Everybody knows in 1905, Einstein declared that light was the maximum speed limit. So he was the first one, Schwarzschild, to actually lay the groundwork for what we think of as a black hole. He didn't use the term black hole. That would come 50 years later, but he did use that groundwork. Now here's what you need to think about, and this is what I've always thought about too. Imagine if you're living in 1915 and somebody said, we're going to crush a star down to a single point. You would ask yourself, how could that happen? What could do that? What could bring on that force? And we have to move ahead in our story over 50 years. We go to Cambridge, England. We get to Stephen Hawking and Roger Penrose, and these two actually quantified something that we know of as a supernova. That's when a dying star explodes. It crushes this core down when it ends at the ends of its life. And these are, of course, massive stars, at least 15 to 20 times the mass of our sun. So Penrose and Hawkins actually came up with a mechanism where you could actually crush something massive down to something small. They had a famous equation. They named it the Schwarzschild Radius in honor of Carl Schwarzschild. We'll be using that in class to actually do what Hawking said in the 60s, and that is anything can be crushed down to a black hole, given the force. The only force that we know of course, is the supernova. Now, we know a supernova event happens in our galaxy about every 100 years. It's not a common event, but it is something that we're ready to see. One more point I want to make, too, about Hawking and Penrose was they worked in reverse. They said if the supernova could crush the star down to the singularity, as they termed it, that must be how our universe started. And I just want to mention something about the Big Bang. We've heard about it. I heard about it when I was in high school. And to see if you're like me, when I first heard about the Big Bang, I wasn't going to argue with it necessarily. It's this idea by Einstein, Schrodinger, Max Planck, the data collected by Edwin Hubble, the great American astronomer. But in my mind, I always wondered what could take our universe and put it in one small space? What could actually do that? And I just, in the late 70s, when I first started thinking about that, I thought, what could do that? So keep that in your mind as we move forward in our story. This is where we want to actually see a supernova event happen. When we get to a supernova, and here's an image of the Crab Nebula. This is a supernova that blew up in 1054. Very few people documented it. The Chinese famously documented it. So did the Anasazi of New Mexico. This was a massive red giant star that was in the constellation Taurus. As it exploded, it imploded, then exploded. All of the heavier elements that we like, things such as gold, platinum, silver, all the heavier elements above atomic number 26 were created in this supernova. If you look into any of these supernovae, that's plural for supernova, you're seeing the building blocks of what our world is today. So they're very important in the evolution of planets and solar systems for sure. Now you may be asking, and I ask this a lot, and I want you as students to be doing this. Is there a supernova in our future? Are we going to see one of these events? And the answer is maybe. We haven't seen a supernova in the northern hemisphere since 1704, back during the time of Johannes Kepler, who we've studied in this class. Now, if you're going to bet on a supernova happening in our night sky here in Medford, of course, you would bet on the star Betelgeuse. You know it in the armpit, the red supergiant in Orion. We still see it tonight. You'll see it in the early spring, and this is being taped in April. And it is that red giant star that you see there. Now, this is through a little 3-inch telescope, so it's been magnified. You can see the color. What you would see with the naked eye would be an image similar to this, where you're actually just having to find Betelgeuse in Orion. Now, Betelgeuse is 1,400 times the mass of this sun. Betelgeuse is not very close. It's 642 light years, so if Betelgeuse were to go supernova, it would have had to have done that in 1378. We're going to get our math team to check that number. But if it were to have erupted and exploded in 1378, tonight you go out, you would see that supernova, and it would be brighter than the full moon. It wouldn't last forever. That light would dissipate, but it would be quite the event. I want everybody who's watching this to hope, to pray that Betelgeuse blows up during our lifetime. That way we get to experience a supernova. That would be an amazing astronomical event. So everybody cross your fingers on that one. Moving along in our story, so Hawking and Penrose set the foundation for black holes. They said they are possible. Supernova could create them. So that started the search for black holes starting in 1964. Well, guess what? Astronomers found a very interesting star in the constellation Cygnus the Swan, a summer constellation. And that star is named Cygnus X1. Going into how an astronomer would actually find a black hole, the first way would be to detect a star orbiting a dark spot in space. And if a binary star's actually partner had gone supernova and formed a black hole, you would see the outer layers of gas orbiting what's called the event horizon around that black hole. As material falls into a black hole, based on Schwarzschild's work and Hawking's work, it's going to accelerate to the speed of light. That's the definition of the black hole. To escape it, you'd have to go faster than light, meaning nothing escapes the black hole, thus the name black hole. About this time in the early 60s, the name black hole was coined by Princeton astronomer John Wheeler. He was describing Hawking's work, and he said, if you were to see a black hole, well, and then he said it would be black. That event horizon would make it black. So imagine seeing material orbiting around a dark material in space. As material orbits the event horizon at the speed of light, it creates, through another one of Einstein's equations, E equals mc squared, the matter orbiting the black hole at the speed of light is going to create an amazing amount of X-ray and gamma radiation. Those are called jets. You'll always see those 90 degrees to the material orbiting the black hole. And that's what astronomers look for. This particular black hole was first discovered in 1964, not verified until 1990. It took observation after observation, data point after data before astronomers were ready to say, yes, we found a black hole in Cygnus, the Swan. So the X-ray jets are the main way you're going to see this. You can imagine a tornado, and what that's called is a torus structure. And that's a very common structure in our solar system. Imagine a tornado orbiting around a point. That's what we're seeing around that event horizon. The funnel cloud coming off the top, that would be the X-ray and the gamma ray jets. Well, astronomers want to know how many black holes are out there, right? These could potentially be dangerous if you got near one. So they started putting X-ray and gamma telescopes out into space. Some famous ones are the Chandra and the Swift and the Fermi, 3 different space telescopes that look for those gamma jets. And those are examples of what a feeding black hole would look like. It begs a question, and let's ask that question. What if a black hole's not feeding? What if it's not pulling in material, creating that X-ray and the gamma ray jet? What if it's just out there in space? Can we see it? Now we go back to Einstein. Einstein, of course, was a great theorist. He said a black hole, if it got in front of a light source, would do what's called gravitational microlensing. That's where a strong gravity field would focus or scatter depending on the angle between the light and the black hole. And guess what? After 10 years, an astronomer in Arizona, Tim Axelrod, discovered the first evidence of gravity microlensing. We see it here. I'll actually show you the actual data from the observatory at the University of Arizona where microlensing occurred, and that is this here. If you look at the top left of this image, you see just a really small star in the Magellanic Cloud, a satellite galaxy of the Milky Way. Notice how the star begins to increase in brightness, and then it goes back to its original brightness. That can only be explained if a black hole drifted in front of that star while the team was taking that image. So in 1999, we found another way to find black holes through Einstein's idea of gravitational microlensing. Well, you take the last 30 years of searching for black holes, and guess what? Anybody want to guess how many black holes we think are in our Milky Way? And this is just our galaxy, our 300 billion stars. Any guesses? Well, astronomers think there's about 30 million black holes in our Milky Way. That may be frightening to you, but think of it this way. There's 300 billion stars and only 30 million black holes. The chances of us being eaten by what's called a stellar mass black hole, very slim, very, very slim. Less than 1 in a million that it'll happen. But as time goes on, these stars will continue to go supernova, especially the supermassive ones, creating more and more black holes in the Milky Way. Let's tie in somebody from Medford here, or somebody who has connections in Medford. So we've been talking about stellar black holes. One single black hole formed from a supernova explosion out in space. Well, what about supermassive black holes? Do they exist? What astronomers call monster black holes, giant black holes that have eaten millions, if not billions, of stars. Well, let's talk about a galaxy. Its name is M87. It's one of the brightest galaxies, even though this galaxy is 50 million light years away. So is this picture that's been taken, The light that left it left 50 million years ago. Astronomers have been bugged by this galaxy for forever. Why is it so bright? What's going on here? What is happening here? No one knew what was going on, but there was one theory that inside of it was a supermassive black hole. Well, a team of astronomers got time on what's called the Keck Telescope. Look that one up. It was the largest telescope. It's on the big island of Hawaii. And the twin mirrors wouldn't fit in this library here at Hedrick. And a group of astronomers, including Dr. Richard Chambers, who is the father of Dr. David Chambers, who's a physician here in Medford. Aha. He and a team used the Keck Telescope to look into M87 and resolve and focus in. And you may ask yourself, where is M87? If you go out tonight, I've got a little pointer here at M87. It's in the constellation Virgo. And it's in what's called the Virgo cluster. And guess what? As they focused the telescope on M87, they resolved and saw stars and gas disappearing into the event horizon of a massive black hole. Here's part of an image of a verification. This is a Hubble shot of stars orbiting around the central black hole. Now, this black hole has eaten 2.5 billion stars. First observed in 1987, verified in 1993. I was teaching a class years ago, I'd say probably 2007, and I mentioned this research. I mentioned this black hole, the supermassive black hole discovered in M87. And a girl in my class, her name was Ashley, said, "Oh yeah, that was my grandfather." We're sitting in the planetarium talking about this. And I just stopped, and I looked at her, and I said, "Your grandfather?" And she said, "Yes, Mr. Black." And I said, "Is he still alive?" She said, "Yeah." And I said, "Well, does he ever come to Medford?" "Yeah." "Would he talk in the planetarium?" She said, "Well, let me ask him." And Dr. Richard Chambers gave 2 talks. I taught 3 out of 4 of his grandkids. They all went to North Medford. And he did 2 fabulous talks about the thrill of discovering the first supermassive black hole. He was a collaborator with a team of astronomers. But what a great to hear a master of the trade talk about his incredible discoveries. Now the next train of thought is, are there lots of supermassive black holes, and how did they get so big? It turns out 99% of all galaxies have a supermassive black hole. The conclusion of astronomers is, if a galaxy has a bulge at the center, that bulge is created by stars and material swirling around the torus structure of a supermassive black hole. So now, when I was young, we just talked about galaxies, clusters of stars orbiting around in these swirling vortex of material. Now we know that these stars are attracted to the supermassive black holes, that the black holes have drawn in the stars, these swirling vortexes, these torus structures, just like a hurricane, just like a tornado. Now, the way you see them as we go through there is when they're feeding, and if you're at the center of a galaxy, you're going to make that jet, that X-ray and gamma jet. We can see that in X-ray. We can see it in gamma rays. We can see it in visual light. Matter will be stuck in those jets. So the implication here is that every galaxy has a feeding monster black hole inside.
In the eye of this cosmic tornado, gas and stars flow into the hole along a rapidly spinning disk. The spinning motion generates magnetic fields that twist around as matter swirls in. These fields channel some of the inflowing matter out into a pair of high-energy jets.
M87, of course, is famous. The image on the left is a very famous image. It's a radio series of radio telescope images. This is from last year. Radio telescopes that see radio waves, and of course, as black holes eat things, it emits all sorts of radiation, including radio waves. The image on the left is actually an image of the event horizon, the point of no return where nothing can escape, including radio waves. Nothing. X-ray, gamma radiation, light, microwaves, nothing can escape from that center there. So this was what's called interferometry, where radio telescopes in South America, North America, Antarctica, Europe, all together pointed at M87. And by doing that and focusing on the same point in the sky, their radio telescope was the diameter of the Earth itself. If you look up interferometry, it's a way to link telescopes together to get better vision. That image on the left there is a famous shot, evidence of the supermassive black holes. We've got to ask ourselves, where did these monster black holes, these supermassive ones, where do they come from, right? How did they get so big? And do they tie anything into to the universe and maybe to the beginning or the end of the universe? What is their place in the evolution of stars in the universe itself?
To grow large, one black hole must draw the other in, close enough to swallow it. Albert Einstein showed how they do it. He predicted that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time.
After the Big Bang, hydrogen and helium were created. That's the beginning of star stuff. So these monster black holes were the early black holes created 12 to 13 billion years ago after the universe was first created. We know through simulations by Tiziana De Matteo and collaborators at Carnegie Mellon that these black holes, we now know they can merge. They can come together. Their singularities can join together, and the black holes can get bigger and bigger. Their gravity strengthens. The singularities, the gravitational attractions increase, and their effects can be amplified. Now, guess who predicted that black holes could merge and that you'd be able to measure these strong gravity waves? Guess who predicted that? Albert Einstein. Einstein said that if two large bodies interacted and united, it would create a ripple in the fabric of space-time that we could actually see. And so this frenzy of black hole mergers, eating everything in sight, caused these supermassive black holes. And of course, Einstein was the one who predicted this, and we want to know if he's right. That's what science does. People make predictions, they theorize, and then scientists collect data, analyze it, and come with conclusions. All science is done that way. You go towards the data collection and the conclusions. Well, when two black holes merge, do they create gravity waves that could be measured on Earth? And the answer is, well, we'll have to test it. And it took over 10 years to build this, but we've got the LIGO, the Laser Interferometry Gravity Wave Observatory. There's two of them, one in Washington State north of us and one in Louisiana. These are the longest, most powerful, most sensitive lasers ever dreamed of, built to measure a ripple of gravity waves from outer space. And guess what? They verified a merger of two black holes in 2015. They tested, retested, and announced to the public a couple of years ago that Einstein was right. Do black holes have a key role in the beginning and the end of the universe? Go back to my initial question. How on earth could we take all the matter of our universe, all the stars, all the planets, all the asteroids, the comets, everything you could dream of, anything you could see in a telescope, how could that have ever been in one place to start the Big Bang? How could you make that singularity, as Stephen Hawking theorized? Well, has anybody got any ideas? How about black holes? Black holes have the ability to attract matter and condense it. So we've got this famous simulation. It's an animation done by Tiziana De Matteo, where you've got she's merging two galaxies, and then in course she's also talks about the merger of the black holes. Her simulation, by the way, she runs a supercomputer. It probably barely fit here in Hedrick Middle School. So she runs all the data that she has on the merger of galaxies. Guess how long it would take two galaxies the size of the Milky Way and the Andromeda Galaxy to actually merge, and for their black holes to consume each other into one black hole? Well, if you run this animation, it's going to take about 2 billion years. So if we look at this time in the universe where stars are going supernova, turning into black holes, and then those black holes are merging, they're eating the stars, we're starting to see where black holes are the key to putting all the matter in the universe into one place. And that one place would be that singularity, that beginning point of our Big Bang. And then once again, we draw back to Stephen Hawking. Hawking, mathematically using quantum mechanics and quantum physics, found out if you have a singularity that reaches what's called Planck density, and that's 1 × 10⁻93 grams per centimeter cubed. That's all the matter of the universe. That matter would start to emit radiation and at some point would explode, meaning that the universe would have an ending point. To me, and I think most of you would agree, 30 years ago we really didn't know how the universe began, how it would end. But by taking black holes and projecting them into the future, we have a mechanism that would draw in all the stars, all the matter, and create a new Big Bang, and then, of course, a new universe. Kind of a cycle, a life cycle. But in this, it's a stellar life cycle. And with that, we've studied the past. What was science fiction? What was, I can remember when I was younger, black holes were sci-fi. Wouldn't it be strange if? Wouldn't it be incredible if these things existed too? There's not only 30 million in our Milky Way, but they're going to actually merge all together at some point. This is theory. It's not proven at this point. This is all the stuff of simulation. But it's a pretty exciting time to study this. Now, I don't want to scare anybody. Is there anybody out there worried about being sucked into a black hole or anything of that nature? I've had my assistant, Blaine Dinky. He has put a couple of numbers on a whiteboard here at the classroom. And we think the Big Bang was about 13.8 billion years ago. And he's written that out in scientific notation. He's also written it out with all the zeros. So that's 1.38 times 10 to the 10th years. That's when we think our universe began. So I've talked a little bit about what astronomers think, when it's going to end. Well, guess what the simulation says? The universe, all the black holes will merge in a Google year. So if you subtract the 13.8 billion years, we've got 1 × 10 to the 90th years left of our universe. And Blaine looked that up. We've got it on a whiteboard over here. You can see that number he's written there. That's a 1 with a 1.3 times 10 to the 10th. Now below, this is how much time until our universe ends and a new one begins. 1 times 10 to the 90th is a novin vigintillion. Does that sound right, Blaine? Yeah. All right. So if I don't know if anybody can check that. I'd like for somebody to check and see if that actually is 90 zeros there. It's a lot easier to write 1 times 10 to the 90th and out all the zeros, right, Blaine? Yeah. Well, as we conclude our lesson, I hope you're fascinated with black holes. I know I am. I've been studying them for every bit of information I can get. I like the fact that they've gone from theory to real life. We can find them now. We've plugged them into our history of our universe. And with that, I'd like to say thank you.